carrying on with momentum, and look, we're doing kinetic energy conservation. So we're doing one more part, and I know you're going, oh, wait, that sounds familiar. Haven't we done this before? Maybe, maybe not. Let's see where we're going. So, when you hear a tennis ball being hit, you hear a noise. Why? Where does that come from? Sound is a form of energy. Where? How? That's what we're looking at, is where does that noise come from? Okay? So you're going to keep that in the back of your head. Now, we've done most of this. We're doing really well. So today, we're going to look at the conservation of kinetic energy. So there's a couple of key words we need to remember. First one being, okay, no, I don't want that. First one being, what is kinetic energy? Oh, we're going to remember some stuff from when we were from a younger age, okay? Elastic collision, that's a new word. We haven't discussed that before. We did collisions and we've done explosions, but elastic collision? Do we mean an elastic band? No. We're also going to talk about what are inelastic collisions. So now we're going to separate our collisions into two different types, elastic and inelastic, and we're going to talk about what that means, because it's actually really important for us. And then we're going to talk about the conservation of kinetic energy. And I'm using the word kinetic very, very, very specifically, okay? Because I'm not doing energy as a whole. Be very careful. So, let's look at what we're going to discuss today. Number one, we've got to remember the equation. EK equals a half mv squared. You've seen that equation before. We'll do it in detail. It's on your information sheet. Yay. Okay? Then we're going to talk about what an elastic collision is. We're going to talk about what an inelastic collision is. And the two are going to go together. So we're going to talk about the consequences of these types of these collisions with regards to kinetic energy. So that's our focus now, all right? What I need you to keep in the back of your mind the whole way through is that momentum is always conserved. There's no exception to that. So, if we look at the question, what is kinetic energy? Well, we should know this. This is stuff we've dealt with. So, when you dealt with Newton's laws, you would have learned a little bit about potential energy because of gravity. So we know there's potential energy, we know there's kinetic energy, we know there's heat energy, there's chemical potential energy, there's lots of types. I'm concerned with kinetic. The word kinetic means motion, means busy, means dynamic. So kinetic energy has to do with motion. For an object to have kinetic energy, it must be moving. So if I stand really still, which is very difficult for me, I don't have kinetic energy right now. When I move, so now my hands are moving, heaven forbid you tie them behind my back, when with my hands moving, they have kinetic energy. My feet don't, because they're stationary in one place. Also difficult for me. Have to always be moving. So I have lots of kinetic energy. How do we work it out? Well, we know, definition first, sorry. Kinetic energy is the energy that an object has due to its motion. Definition, learn it, okay? That gives us the equation EK equals a half mv squared. So let's just remind ourselves what all of these mean. EK stands for kinetic energy. We know that kinetic energy is measured in joules. It's a capital J, and it must look like a capital J. Please be careful. Often when I'm marking, I know some of you have the most beautiful handwriting, and you write these beautiful J's, but they look like a lowercase. It's just a very big lowercase. I can't give you the marks. It must look like a capital, okay? Half is a half, it's the value. M is mass, which is measured in kilograms, and V is velocity, and that's in meters per second. What we need to remember is kinetic energy is a scalar, has no direction. Also, you can't get a value for kinetic energy on its own. That's a square. Even if the velocity is negative, it doesn't matter because we're going to square it. And the square of any negative number is a positive number. So you cannot get negative values for your kinetic energy in this section. If you do, you've made a mistake. Go back. All right. So now, is kinetic energy always conserved? And I suspect that some of you are you're at the TV going, energy, yes, we know, because we've done this lots, it's been drummed into you, that energy is conserved. We cannot create energy, we cannot destroy energy, it's always conserved. But the full statement of the conservation of energy is this: energy cannot be created or destroyed, it is simply transferred to another type of energy. So there's the proviso. Yes, energy as a whole is always conserved. Sometimes it doesn't feel like that because we can't always put our finger on what the energy has become. Kinetic energy as a specific energy doesn't need to be conserved because the kinetic energy can be transferred, it can be transformed into another form of energy. Okay? So when I run, don't do it often, I have kinetic energy. Eventually, that kinetic energy results in me perspiring a lot and using up other energy in so I get quite hot actually. I go all red and pink and just not pretty, and I'm hot. So the kinetic energy I had is changing into heat energy on my face. It's not pretty. We don't do it often. But we can transfer it, okay? When we have an object that's been thrown up, the kinetic energy, you learned this in a previous year, the kinetic energy gets changed into potential energy when it gets to the top. So we're changing kinetic to potential. We can transfer the kinetic energy, so it's not always conserved. It's possible for it to be conserved, but it's rare. It's very, very rare. All right, so that gets us to this inelastic collision. And in elastic collision, the total kinetic energy of the objects is not conserved. So when we have what we call an inelastic collision, the kinetic energy of all the objects before they collide and the kinetic energy after they collide are not equal. It's not equal. The kinetic energy doesn't get lost, okay? It's transferred to something else. And when we put this in an equation, remember that sigma means sum, so the total kinetic energy initially is not equal to the total kinetic energy after the collision. Inelastic. 99% of all collisions are inelastic because we live in a real world. So when two objects collide, even like when I clap my hands, the kinetic energy gets transferred into sound. Sound's an energy. Sound is a form of energy, so we transfer in the kinetic energy. Then we get elastic collisions, very rare. Here, my kinetic energy is conserved. So the total energy the system has before the objects collide is equal to the total energy after they collide. Here, we cannot have an explosion, so objects that are together that then move apart, where the kinetic energy is conserved. That is not possible. All right, so just be careful with that. These have to be collisions. Here, my initial kinetic energy will be equal to my final kinetic energy. We're going to do some problems near the end of the program, and I'm going to show you how to work with this. This statement becomes a proof. So we have to remember how we do proofs in maths. Okay, maths can't, your maths ability, your maths skills can't be left at the door when you write a physics paper. They've got to come with you because they're important. Okay, so we've discussed the conservation a little bit. We're going to take a short break, and when we come back, we're going to look at how we can recognize elastic and inelastic collisions. Okay, so we're going to take a short break, and we'll be back in a couple of minutes. Welcome back, everyone. Now we're going to get into the nitty-gritty. So we spoke a little bit about elastic collisions and inelastic collisions before the break. Now let's investigate some of them, okay? So we know we're busy with conservation of kinetic energy. So now what we're going to do is we're going to go, what happens with kinetic energy during an elastic collision? So let's go and play, okay? So here's our simulation, and I'm not worrying about the momentum vector diagrams while we do this because I'm not really concerned about that. But what we're going to do is we're going to look at the values, okay? Now, I've got velocity here. And I've got mass, and what we're going to do is we're going to go back and forth between the two, between the black screen and this one, because we're actually going to do a calculation with this, because it's important for us to do that. So we're going to take note. Now, I know they're not moving at the moment, okay, because I haven't pressed play. But at the moment, we have my block A, the bluish one, number 1, which has a velocity of 1 to the right, which is my positive direction. So I'm going to take a note of that. And block 2 has a velocity of minus 0.5 because it's going in the opposite direction. And over here, I've put, so on this, actually, can I show the kinetic energy? There we go. I don't even have to do the calculations. Look at this. My total kinetic energy, that's what's in the bottom right-hand corner. So if we had to work it out, which we're not going to do now, I have 0.44 joules. So what they've done is they've taken the kinetic energy of block 1, which is a half mv squared, and they've added it to the kinetic energy of block 2. Remember, I said to you before the break, you cannot get a negative kinetic energy. That energy is very small, and I'm okay with that, because if we look at the velocities, they're not very big, and the mass isn't very big. So I'm not expecting a very big kinetic energy. So one thing to keep in the back of your minds is when you calculate the kinetic energy, look at the object, look at the size of its mass, and look at its velocity. And say to yourself, does it make sense that the kinetic energy is that big or that small. Unfortunately, I can't tell you that it's always going to be very big or it's always going to be very small. Depends on the objects. So, let's let them collide. There we go. Oh, look at that. The total kinetic energy didn't change. It's elastic. I'm telling you it's elastic. I've also said to you earlier that this is very rare. So, so rare. The closest I can give you as an example for an elastic collision is a collision where, so something like snooker balls on a snooker table, because they're very hard, and the snooker table has a felt on it that gets rid of friction. Okay, it makes it nice and smooth. But when those snooker balls hit each other, it's close to an elastic collision because of how hard they are. But it's not quite. In the real world, we don't get elastic collisions because whenever two objects hit each other, we hear a sound at the very least. Even if it's a tiny, soft sound, you will still hear something. Also, there's a heat transfer, okay? Because when they smack each other, we get heat transfer. Elastic collision, that doesn't happen. So let's just see if that's always the same. So let's reset this. Let's make the mass of my first object a bit bigger, okay? I've made it 2. Look what happened to the total kinetic energy. It's now gone to 1,44. I've still got it as an elastic collision. Let's let them, oh, look at that. The 2 goes off with lots of energy. 1's going very slow now because 1 was very big. The momentum, the total momentum stayed the same, and the total kinetic energy stayed the same. So before the collision, we had a total kinetic energy. After the collision, we have a total kinetic energy, and it remains constant. Let's look at what happens. Let's make the initial velocity of this object 0. In other words, now we're going to see still an elastic collision, and watch what happens. Total is still 1,25. Did you see that? Look at the total. It's 1,25. All the kinetic energy in the system's coming from number 1. Number 2 has no kinetic energy because it's stationary. When it hits number 2, some of the kinetic energy from number 1 gets transferred to number 2. Number 1 keeps going, but my total is still 1,25. Number 1 goes slower because of the collision, and number 2 speeds up, but they still go. Let's see what happens. Let's make number 2 the same mass as number 1, but now it's stationary. Okay? My total is still 1,25. Let's see what happens. Number 1 stopped. Same mass. Okay? If you go and look at a thing called a Newton's cradle, it's a good thing to look up online. It's those toys with the 5 little balls, and they swing backwards and forwards. Okay? Those are close to elastic collisions. It's this concept that because the metal balls have the same mass, they can transfer all their velocity to the next one, so they go backwards and forwards like this. But you hear a sound. So eventually, they slow down because their kinetic energy is getting transferred to sound. So it loses it. And there's air resistance. We're ignoring air resistance, okay? This is a completely isolated system. We're ignoring air resistance, okay? And I could do this all day, but we're not going to. So when we look here, so for elastic collisions, my total kinetic energy before they collide has to be equal to the kinetic energy after. When we do calculations, this is something I have to prove. We do not start with that statement. So that means we have to go the sum of the kinetic energy before will be equal to a half mass of the first one times its initial velocity squared plus a half mass of the second one, initial velocity squared. Okay? We have to do that calculation first and separately. Then we can do the calculation for, oh, there should be an E there, after. And that would be with my final velocity, with my final velocity of number 2. And then once I've got those two values, I can compare them. All right? And only when I compare them can I say they're equal or not, and then say it's an elastic collision. Please, this is very important because you often just going to start with they're equal, and then the maths goes out the door and something goes very wrong, so we're not going to worry about that. Now, let's look at an inelastic collision. So now we're going to go back here. Let's reset this. We're back at what we had here. Now I'm going to change whether it's elastic or inelastic, okay? Now, if you look at my little scale over here, no, stop it, over here, I can go to 100% inelastic. Okay, we're not going to, no collision is 100% inelastic. So I'm going to make it a percentage. It doesn't actually matter. I have my two objects. They're going at the one stationary, one's moving. Remember, when this was elastic, number 1 stopped and number 2 kept going. So let's see what happens if I put them together now. Oh, now that's more realistic. Okay, watch again. We've made it an inelastic collision. They keep, number 1 keeps moving now. When it was elastic, number 1 stopped. Okay, now it keeps moving, which is more likely going to happen. Let's look at the kinetic energy. Before they collide, it's 1,25, the total. After they collide, it's now 0,68. The kinetic energy got smaller. In reality, if we could hear this, the difference in the kinetic energy, the fact that it got smaller, is sound. You would hear them colliding, okay? There's going to be friction between them, so you'll have heat. If these were metal balls, you might see light, okay, because they're rubbing against each other. Let's see if that's always the case. So let's make number 1, 1 kilogram, okay. Let's make number 2 moving in, say, the same direction as number 1, and it's going at 1. So they have the same velocity, and let's see what happens when they collide. My total kinetic energy is 1,75, so let's see. Oh, they're not going to collide. Why won't the balls collide? Well, they're going at the same velocity. One's never going to catch up. So let's reset it, okay? Let's make it, so let's make number 2 go slower. Let's make it 0.5, okay? And let's give 1 a bit of a fighting chance. So I'm going to put 2 a little bit further, closer to 1, all right? And there's more space for it to try and catch up. Total kinetic energy, 0,81 joules. Let's see what happens. There we go. They collide, but 0,73, so we lost energy again, and they move on. Now, with all the ones we've done so far, we've had them end up going in the same direction. But what happens if they change direction? Okay, so let's reset, And I'm going to do this, and let's change that one to be going at minus 0.5. Okay, let's see if it bounces. We got 0.81 kilojoules, so here we go. It doesn't matter that it changed direction. But can you see that by changing direction, we had a much bigger loss in kinetic energy? So here, the original was 0.81. When they collide, they have a much bigger, now becomes 0.08. So in other words, when two objects collide with each other and they go in opposite directions, more kinetic energy is lost. There's a bigger transfer of kinetic energy, okay? And that's always the case. So let's go here. So when we have an inelastic collision, this is the concept. Kinetic energy before is not equal to the sum of the kinetic energy after. Now here we need to be careful. Most of the time, the kinetic energy before will be smaller than the kinetic energy after. It's not always the case, so I can't say bigger than or equal than. They're not equal. Just like with an elastic collision, in order to prove this, I have to work out the total before and the total after, and then compare them. Okay, we can't start with the statement. Very, very, very important. That, okay, brings us, to the end of this part, okay? Lots to think about. In the next part of the program, we're going to do some calculations. So take a short break, and I'll see you in a couple of minutes. Welcome back. We're in the last stretch. We can do this. Now we need to do some calculations, okay? So we still look in the conservation of energy, and we're going to look at a couple of examples. Here's the first one. We have a ball of mass 1 kilogram moving east at 2 meters per second. Another ball of mass 1.5 kilograms is moving west at 1.5 meters per second. The balls collide head-on. After the collision, the 1 kilogram ball rebounds. Rebounds means that it changes direction. So it was going east, now it's going to be going west with a velocity of 2.05, and the 1.5 kilogram, rebounds at 1.2. So it was going west, now it's going east. They've been really nice in this question because they've given you both before velocities and they've given you both after velocities. There's a reason for it because we're trying to just get to the kinetic energy part of this, okay? So what's the situation? We have a 1 kilogram block, okay, that's moving east, and they said to me that it was moving east at 2. It then collides with a 1.5 kilogram block that's moving west at 1.5. Then they collide. There's my collision. I'm going to do the after over here. The 1 kilogram rebounds, so it's going in that direction, and they said it was 2.05. And the 1.5 rebounds, so now it's going east, and let's just check. It said it was at 1.2. So that's our situation. Just because now we're going to be looking at kinetic energy doesn't mean we can ignore direction, okay? Velocity is still a vector. As a vector, it needs to have direction. We need to make a decision. I'm going to make east positive simply because, so that's my positive direction, simply because east was given first. If they had said block A was going west, and that was the first thing they told me about, I would have made west my positive direction. You can choose, it's up to you. I just like to stick to something that's the same with every question. Original direction, positive. So, that means for us, because that's going west, the 1,5 is going at minus 1,5 meters per second. And after the collision, the 1 kilogram is going at minus 2,05. Always write that in, because it's these little things like the direction, like the negative, that costs you marks, because it's considered the simple things. Sometimes it doesn't feel like it, but they are considered the simple things, so we've got to take it into consideration. Now, question says, calculate the kinetic energy before the collision. We're leading you a little bit. Before the collision, so sum of the kinetic energy is going to be the first ball's initial velocity squared times its mass times a half, plus a half times the second ball's mass times the second ball's initial velocity squared. We have a half times 1 times 2 plus, and that's squared. Please don't forget the squared. I see that all the time. In fact, I almost forgot. A half, and then it's 1,5. Now we take note. Its velocity was west. West is negative. I have to substitute in the negative. I know that when I go 1.5, negative 1.5 squared, I'm going to get a positive answer. That's not the point. Velocity is a vector. When I substitute in the vector, I have to keep the negative as part of that. Now, we're going to use our calculators. I could do the first part of the sum in my head, but I can't do the other because of the 1.5. So, let's just put this over here so I've got everything. So I have 0.5 times 1 times 2 squared plus 0.5, whoopsie, let's make sure you got the 5, 0.5 times 1.5, 5 times, let's do the bracket, minus 1.5 squared, close the bracket, equal. I get a positive answer, and it's 0,3125. So, here I've put 4 decimal places, because it is a very small kinetic energy. The instructions in your exam are to round off to at least 2 decimal places for your final answer. Yes, this is a final answer, but because it's exactly 4 decimal places, I'm going to keep it. Sometimes in these questions, the change in energy is so small that if you round off too early and have too few decimal places, you won't see it. So just be careful, all right? I'm going to keep the 4. Now, that's the first one. So that's the kinetic energy before the collision. Now they say, oops, I skipped this page, the kinetic energy after the collision. So I'm going to do exactly the same thing. I'm going to calculate, but now I'm looking at final velocity plus final velocity squared. So that means I've got a half, and the first ball was 1 kilogram, and now after the collision, it's going at minus 2,05. Remember, it changed direction. Then we have a half, 1,5, and now this is going at 1,2, and it's squared. There is no way I can do this in my head, and my maths isn't bad, okay? Please use your calculators. Now, there probably is someone or more than one of you who can do this in your head, and that's impressive, okay? I can't. So, calculator. Here we go. Let's clear what we had. So we're going to go 0.5 times 1 times negative 2.05 squared. We're going to add that to the 0.5 times 1.5 times 1.2 squared. There we go. And, ooh, I've made a mistake. Can you see? I got a negative answer, and I shouldn't have. So let's see where I would have made the mistake, and I think it's here. Okay, and it's important that we get this. So what I'm going to do is I'm going to take that negative away from that, and I'm actually going to put the square there, so it's part of the bracket. Okay, much better. Positive answer, it's what I expected. Oh dear, that's not what I expected. So, we need to go look at some things again, because when I look at this, I go, first of all, now I'm going to get, and I want you to see this, okay? Oopsie, wrong way. Here, we got 3, let's just go back to this, 3,18125. Now, that makes sense. If I go back here, I got 0,3125. Something's not right here. So let's do this one again. I think what I did, okay, is I didn't square that 2. And that's fine. This is why we go back and check. So we've got 0.5 times 1 times 2 squared plus 0.5 times 1.5 times minus 1.5 squared. There we go. Okay, now that makes more sense. Okay, so now we've got 3,685. So let's just fix this. And you know what? We all make mistakes, and it's fine. It really isn't a problem. So let's just go back and look again. 3,685. So let's put that in. Not with the eraser. Here we go. 3,6875 joules. Okay. Now, how did I know I'd made a mistake? Because it collided, not exploded, and the kinetic energy got bigger. Not going to happen in a collision. It's not possible. Okay? And it's a big difference. So I knew there was a mistake, and it's important that you see that. So then it went to 3,1825. So now it's got smaller. Not by much, but it got smaller. We're okay with that. Next question. Is the collision elastic or inelastic? And then they say, explain your answer. It's an easy explanation. The kinetic energy before the collision is not equal to the kinetic energy after. It doesn't matter whether the after kinetic energy is bigger or smaller than the before kinetic energy. That is not the point here. The point is they are not equal. So, the answer is, it is an inelastic collision. Why? Because the sum of the kinetic energy before is not equal to the sum of the kinetic energy after. Explanation. Nice and simple. Didn't want a lot, didn't need to explain anything. They just wanted to know why we know it's inelastic. Now comes the next part. Now they ask you, why did the kinetic energy change? What they're asking you here is this. Because we know energy is always conserved. We can't lose energy. It changes form. Here, the kinetic energy didn't stay the same. What has happened to the kinetic energy? So what we want here is the kinetic energy is transformed into sound. We hear the collision and heat, okay, because there'll be friction. Definitely those two. Plus, now the third one is a little bit different, and it can be transferred into what we call deformation energy. This is a new one, okay, and this one's a hard one. No matter how hard the objects are, let me just put this down. When they collide with each other, they will deform a little bit, okay? They squash. That squashing takes energy, takes effort. So that's the deformation energy, okay? Even hard objects deform a little bit, okay? Everything does it, especially if they hit hard enough. You just can't see it with the naked eye. Sometimes, we can also get a transfer of energy in the form of light. Okay, that's not going to happen often. It won't happen with, it really only happens if they're metal. Okay, because when metal strikes metal, we can get sparks. So sometimes there's light, but really there's always going to be sound, there's going to be heat, and there's a little bit of deformation energy. All right, so that's where the kinetic energy went. Now, and I've mentioned this, is it possible for the kinetic energy of a system to increase? Everything we've done so far today has shown the kinetic energy getting smaller. So now we've got to go, okay, if the kinetic energy increases, it's definitely an inelastic collision. But for the kinetic energy to increase, it means that the velocities need to increase somewhere. And it's absolutely possible when there's an explosion, okay, like a gun. Because if we have two objects, so the answer here is yes, okay? If we have two objects that are together, so they're stationary together, this initial velocity is 0. So at the moment, this system has no kinetic energy. If I now exert a force on them, so say I push down on them or there's a spring between them, and I let that go, and now the two objects go off in a different direction, so they split. What happens now? Now, they both have a kinetic energy. It doesn't matter that they're in opposite directions, because remember, it's a square. So they just disappear, but now they didn't have. So over here, my kinetic energy is 0 at the beginning. Now, it absolutely is going to have a kinetic energy. That should actually be bigger than 0. It's going to increase. So, what am I telling you here? Please be careful. If it is an explosion, so the two objects stay were 1 to start off with, it is possible for the kinetic energy to increase if they were stationary at the beginning. When we've got two objects that are colliding, okay, then the kinetic energy can't increase because we're going to lose to sound and that sort of thing. Why am I telling you this? Because I don't want you to get a fright when you do a calculation and you end up increasing the kinetic energy. Because it's possible. Just look at the whole situation. Look at it in context. Okay, so what have we learned today? In an elastic collision, an inelastic collision, the total kinetic energy is not conserved. Total kinetic energy before is not equal to kinetic energy after. For an elastic collision, kinetic energy is conserved. Total before equals total after. Very, very, very rare. Okay? You're not going to come across those often. And that brings us to the end of today's lesson. Hopefully you've learned a lot, and that's all I have to say for today, so I'll see you again next time.